Good afternoon, everyone. My name is Dr. Kamel Siddiqui. I am the Associate Professor for EC Department. Like now, I've been servicing in IT. Uh, my today's PPT is on FPGA design using Verilog HDL. The main concern of using FPGA design for this domain because this is one of the outcoming technology that is being used in versatile field. So my concept of designing with HDL was have the knowledge of hardware description language and using Verilog, and Verilog is very commonly used in India and US. Okay, so let's begin with FPGA design. So first of all, I just wanted to let you know what an FPGA is. FPGAs are basically free programmable gate arrays. Like how we have ICs, FPGAs are also the plug-and-play devices. Now it comes with variety of features like simulation, synthesis, testing, and having the test bench done on the go to market concepts that basically trades with our costs, and that's why most of the time domain will be revealed, like we are very ready to serve to the market. So like not today's PPT, I'll be discussing on typical FPGA design flow, types of FPGA devices with brief architecture, data of FPGA devices, starter board details, and Verilog main design codes. So why I'm concerning more on Verilog main design, because how it is helpful in FPGA, you already know. Okay. So one of the main factors, like how we have the design verification, is actually the main concept of the FPGAs engineers are. So what we have is design verification. Under this, basically we have functional simulation, static timing analysis, timing simulation, in-circuit verifications. So these are basically, I've drawn this slide based on the job prospects, mostly for the junior engineers when we are coming out of an engineering or an MTech after your degree. So basically what happens in design verification, we design an entry as how we done in IC environment or Vivado, let's say. Then we have design synthesis. This is how what we actually being taught up till this level in our undergrads and postgraduate levels. But design implementation and download to FPGA devices very readily knows, like most of the students doesn't know these fact, and they are very much novice in producing this at the interviews level or somewhere in the hands-on. Okay, so what happens is after design implementation we do the timing simulation, but back annotations are very important because this is the error feedback topology that's being used in here. Okay. So let's begin with the architecture of FPGA. What FPGAs are being more utilized as compared to custom logic or PLD design, that is programmable devices, is because these are the three different families. That is nothing but FPGA architectures, CPLDs, and programmable logic devices. The only concept which is more in demand is how we are managing the time with the trades. Like if you are managing time with trades with hardware architecture, that means one of the best design you are being utilized for. So under this, let us discuss configurable logic blocks, lookup tables and flip-flops, embedded memories, variety of IO standards, and digital phase lock loop. Digital PLL is very much required in Xilinx or VIC. Okay, under Altera FPGA Designs, that is one of the, actually I'm talking about Xilinx first. So FPGA has FPGA is nothing but a volatile device. This is not because when we are placing onto the device and we are programming it and we are reconfiguring it according to applications and then we are removing it, it becomes a volatile. Okay, that's what the most of the volatile devices comprises of. We need to manage the memories. Okay, in this, first I just wanted to discuss about the associated memory devices needed. It's a one-time programmable, because if you take the example of XC17 series and XC18 series, these are all OTPs. It is one-time programmable, because what happens after the plug-in device and when you try to simulate this and when you're trying to perform the whole synthesis operation until time enclosure, what happens at the end, you get, if a single error gets, again you have to reprogram it. Okay, but for doing the reprogramming, you have to be taking on the device again, replacing it with our new programming language, with our new programming codes. That's why these concepts are known as OTPs, one-time programmable. Okay, So all X7, XC17 and XC18 series are comprising of the same concepts. Let's look at the block. Like basically, these are the four important concepts that any of the FPGA blocks requires. That is nothing but CLBs, that is configurable logical blocks, and digital clock modules, DCM. These two, in synchronizing with your logic, with your clock cycles, produces one of the important effect on volatile designs. If your CLBs along with your lookup tables, when you try to mold with your digital clock module, then only that they could comprise and they could feasibly produce your design. So if you look at the diagram on the left hand side, we have IOBs, that is input output blocks, and these are nothing but all your codes that is being multiplexed. Okay, and in order to manage this, you need some block of RAMs, and thereby you can configure all these devices on your FPGA design. Okay, so one of the aspects which I'm targeting based on this application, on this presentation, is mostly on the academics role. So if you look at the board design, these are the one of the basis 3 design by Xilinx. This is the basic concepts. If you look at the on the green blocks, that actually have switches and have some LEDs with LCD display, that is probably 4 7-segment displays. Okay, so we have VGA connectors and RS232 cables across, and we have some extension connectors as well in order to connect any of these sensors in design according to based on your applications. Okay. So I've given you top level and the down level design as well. These are the basic concepts of what the student should be knowing whenever they try to design and make an application, because there are usually a lot of applications which are there in the market and they are very much useful into the market, but students are more targeting on IT devices rather than FPGAs and electronic devices. Anyhow, the application and how the project being performed is something based on the research proposals. What I want to insist on this is because most students should be capable of understanding this nomenclature of FPGAs. Thereby, they can hold the projects and imbibing IT stuff into electronics is one of the need of the hour. So these devices, like the one which I am showing you right now, is one of the commonly used and mostly used in academics at the moment. Probably if you say like in Cambridge, in Harvard, this is what they're targeting now. Forget about Spartan 3, to be honest. Like this is what most of the typical Indian education are prescribing, but Spartan 3 is somewhere like 15-16 years back. Okay, so this is what I'm talking about, is innovations in FPGA technology. Okay, what we do actually is we configure a file, and that's nothing but it's a non-volatile memory anyhow. So we have to have a secure flash memory for this. So thereby we can store the data. Okay, availability of the chip, analog to digital domain, and MOSFET triggering. Okay, so in ADC designs, okay, MOSFET triggering is very common, and that based on any availability of the chip design. This is what FPGAs are based on, one of the commonest applications. Okay, both these devices are introduced by actel and ARTIX now. Actel ACTEL and ARTIX ARTIX. These are one of the most commonly and most readily used providers of FPGA at this moment. Okay, and let's have a so this is a typical development board designs there, where FPGAs from Xilinx, ARTIX, and basis 3, which are very much academic to be academics provision. It comprises of more than 3 lakh gates. Just imagine 3 lakh gates means how the lookup tables could be and how your design should be capable of taking more complexity, and so we should have such designs in our whole. Okay, so I have basically, this is the chart which I am trying to produce in order to compare different families of actels So if you see APA 150, that's my fourth column. This is the most commonest used and most prescribed one for the academics, and this is what actually most of the projects are being consumed from, and this is one of the uh, designs what most of the engineers, the verification engineers would use, and they prefer these designs. APA 450. It has more than like around 4,50,000 gates and almost 13,000 gate registers, and embedded RAM is more than 106 kilobytes. Embedded RAM blocks more than 48. Okay, PLL2 base lock loopers 2. Okay, it has the provision of JTAG ISP, maximum users of IOs, maximum clock range of 48. Okay, and PCI, yes, PCI is an inbuilt. Okay, and this is one of the commonest used design in Altera technology. Okay, so let's jump into how Verilog HDL is being more compatible with such FPGA designs which are common in market these days. Okay, so let's jump into how the HDL being make use of FPGAs in modern world. What actually we are trying to do is we are trying to describe a language. It's not a high level language though. It's just a HDL because we are asking the wires and the connections to listen our algorithms. Basically, they are following, they are abiding what we are trying to write into the modules. Okay, so basically, what we have is a module. Any block of FPGA design can be module. It can be module by an HDL. It could be VHDL or Verilog. Why I'm more stressing on Verilog is because this is the most growing language in India, and it is most commonly used in most of the companies here in, let's say, Xilinx, Hyderabad, Honeywell, Altera, Mentor Graphics, Model 7. Most of them are using Verilog, and the same language is being used in United States of America. Apart from the different, like VHDL is most common in Australia and Europe, but here in Western countries and India, we are providing service with Verilog. So the main concept is how the design entry should be. Okay, it's a module. It's nothing but just a black entity, and we are writing a module anything with the signals, the wire, the registers, input, output block, multiplexers. We have synchronizing clocks. Again, in the same module, what we do, we create the source and then we write the module. Again, in the ISIM, that is the simulation environment, we write the test bench. Okay. Combining these two, we produce timing constraints. We write the timing files. We do the synthesis and simulation. Then we generate the report. This is how the list should go on. But how we are trying to achieve with the academics is only by showing them the simulation. That is the beginning part, to be honest, for the engineers who are trying to abide by the rules and trying to get a job after completion of the engineering or MTech levels. Okay, so what we do is we write the HDL schematics, and HDL schematics again comprise of combinational block with sequential block, FSM, let's say. And what we tend to do is make use of inbuilt libraries and for rapid prototyping. So why we need libraries? Because libraries are the self-programmed contents of modules already built in, where we need to just pick those libraries in your programs and make them work under your work folder. Okay? That's how you constitute, like you manage all your modules with your libraries and make them synchronized. Okay. In order to design these algorithms, what you basically requires is your basic understanding of combinational block. Like, let's say if you are trying to design a filter, how your memories should be. If you're trying a simple adder or subtractor, how your algorithm should be. So one of the complex algorithm, let's say Cordic one, like Cordic, that's a digital computer of convolution, rotationally directional algorithms. That is Cordic, and this is one of the complex algorithm. But still, if you see, it's nothing but a amalgamation of combinational and sequential circuit. That Verilog really helpful in such designs. Okay, then after the performance of this and finishing of this design, we do the simulation. And after simulation, we need to carry out synthesis part for our onboard design. Basically, what after simulation, basically we are saying that our design is ready. And while synthesizing, we comes to know like how many gates are being involved here, and then that generated report is very important. Okay, based on this, we try to dump that program on an FPGA, and that's nothing but this is what the emulation and development boards are commonly used for. Okay, this is one of the next level of the simulation is nothing but placing and routing. Okay, people actually call it as routing, but it's routing actually, placing and routing. So what we do is we configure all your combinational configure logic blocks CLBs based on your timing diagrams to have proper routing. Basically, your routing according. This is you can do physically because the EDS environment are so much user friendly these days. Like we are manually, you can select on the simulation board and you can take the wires. No need to design a new PCB for this. You can just route them according to your wires. Okay, so the design flow as such discussed with your academics is totally different. In fact, with the modern style, you should have a mapping. That is nothing but I'm talking after the place and route mapping. Check to see used FPGA resources because what are the resources you are using is really have a hold on your budget. So that should be one of the important concepts. Then generative bit file, that is one of the easiest way because this is what we are being students are being taught in the engineering level and MTech level. And generate MCS file, that is microcontroller source file. See, MCS file, the name has been given at MCS, but it's not exactly the microcontroller. It is the format of MCS, the file that is being generated. Okay, that we have to load while doing any operations like memory and sequential designs. And after that, we have to connect to FPGA prototype board via JTAG cable and configure the device. So JTAG cable, this is the commonest way of rearranging. If you see any of the embedded systems boards as well, what we do, we actually just connect to one of the means that is nothing but the JTAG board RS232 cable. There are many other services. Now even the self system on chips boards are being so much easier that you can design and Xilinx codes on the same board and you can configure. Okay, FPGA design implementation. After debugging using Xilinx, why I'm saying Xilinx is because it is the most commonest open source device. It's not open source, but it's readily available for the engineers. Let's say the license free version, Vivado, that you can actually have a design for using this Vivado. Setting the user constant file that is UCN, that is what actually required for testing. And instantiating FPGA resources in Verilog, the instantiating part of the FPGA. Okay, so debugging again, we are trying to access the variables, registers and wires in the proper place because whenever you're writing a test bench, your registers becomes the wires and wires become the registers. So this is done by Vivado in Xilinx, and the same concept is done by signal trap in Altera. Okay, identify the variables to be accessed along with clock. Okay, so this is one of the logic what you're trying to achieve while using your design. You should know what the variables to be accessed while if you are finding any errors or debugging concept involves. Okay. Specify the samples needed. Limit decided by embedded memory size. Okay. You cannot have n number of tabs in your filter. This is one of the concepts which I'm trying to tell you. So you should know what your modules are. Okay. Let us begin with the Verilog codes. I think this is the second part of your design, like my PPT. So what a module is. Okay. This is what I'm trying to explain in this design. This is where actually it's like black entity where the input and outputs are being concerned. Like this is where we are trying to show what is coming in and what is going out. Okay. This is the main. It's like an entity. Okay. And while defining the module, you should have an inline after the module, and you should give a space so that your mode of the data should go inside that space. Okay. So here I'm using inputs like clock, write control in, read control in, address in, write data. So basically I'm designing a simple data memory here. Okay. So while doing this, I'm using a parameter, this is nothing but a constant, in order to perform a memory delay. For any of the functions to be happening at the output side, if I need any delay, I should be giving here at the parameter. Parameter is the keyword in here. Okay. So how do we assign the inputs? So this is the simplest of the task. Like give the input values, write the variable, and just semicolon. Okay. If you look at the input line address in, I'm using 31 is to 0. That means 31 down to 0. That is my bit length actually. So address in is my it's just a wire that is having 31 down to 0. That is 32 bits address length. Okay. In the same way, write data in, that is the data which is going inside is nothing but again 32 bits of address. Okay. I'm using 4 down to 0, that is 5-bit address, word address. Okay, it's a register. Okay, so the difference between the wire and register is wire is nothing but a connection, register is nothing but still a wire, but it holds a value. It retains a value. It's just not a connection, it's more than the value of the wire. Okay, so how we allocate a memory space? So in order to allocate a memory space, the main syntax is have a register. Okay, define the register syntax, like how much bit long the memory array is. 32 bits. That's why I'm giving 32 down to 0. But you see, I'm using 32 addresses. That's why I have mentioned at 0 to 31. So that means I have 0 to 31 addresses starting from 0, and my bits are 31 down to 0. Those are bits. That means I have a huge memory of 32 rows and 32 columns. Okay. 32 rows define the memory addresses, and the columns decide the width of the memory. The syntax of reading any of the file as a text is initial, begin, and end. Initial, begin, and end. So you should be very much aware that initial, begin, and end are the keywords in where if you want to suggest or write anything in Verilog code, this is the main 3 lines which are being used. Like this is how the syntax should be. In initial, begin, and end. In the under begin, you need to write $read memory h, and in parenthesis you need to describe the location of your text file, the type of register we are using, and how long it is. It is from 0 to 30. Okay, that is $read mem h data.text memory array 0, 30. Okay, here I am giving a little logic like how and why my data out should appear. So I am using a if statement in here. So what I'm writing is, if my address bit, that is 31st bit of my address in, and my address in is greater than 7C, that is nothing but it's a 32-bit of address hexadecimal format. If it is greater than 100007C and read control is low, see, it's not of read control that n underscore n. So it's not of read control n. That means if my 31st bit ANDing with my address in, that is greater than the mentioned hexadecimal format, and if my read control in is low, then my data out should appear like this. What is that? 32 bits of unknowns. That is why I mentioned XXX. Else my data out should be my memory array with the defined word address. That is what the word address. That means my word address actually giving a specific memory location with them. So that's how my data out. So how simple it is now. So just you need to write the logic under the initial begin statements, define your if loop, and then end it. Okay. So anyhow, in order to recall this, whenever you are using any statement with the synchronous with the clock, you have to write the positive edge of the clock. That means your clock should either works on positive edge or on the negative edge. So the main statement of Verilog is POSEDGE clock, POSEDG, POSEDGE clock. Okay, begin. Then I'm writing a memory delay. That's how I showed you, like I have given it 20, nanoseconds of delay. I didn't mention the nanosecond, but it's a delay of 20. If my write control n is high, that's the concept of writing sensitive statements in parentheses. If my write control in is high, my memory array address should take the data in. This is what is equals to write data in is all about. No. That means my write control, this is how we write actually the memory, right? If my write control signal is high, my word address should take the what and data I'm sending in. It's just writing, it's not reading. That's why if write control in is high, my memory array word address should take this value, and this the end of the module, and this is the end of the program. Okay, now before I end up with this, so how this Verilog code is being, I've showed you a very simple way of logic, like how FPGA Design are being taking this Verilog codes into their modules, and setting up these modules, so that you can easily configure all the blocks. Whenever you write the codes, they look up into the lookup tables, and these lookup tables basically what they do is they actually synchronize with whatever your logic you are trying to explain to the blocks. And this is where your FPGA designs comes into place. And this is again a non-volatile memory, a non-volatile logic. You can just place it, group it in, reprogram again and again, place it inside your devices. So mind you, one of the important FPGA design concept here in Hyderabad is the metro cycles, metro lines, which are being run all over heads nowadays, are being worked on FPGAs. How can they manage the times? It's only by using FPGAs. Okay, so this is the end of my presentation, my first presentation anyhow. So I will be happy if I can have feedback on this. Thank you.